Okay. Good afternoon, everyone. Today is our 9th of 10 lectures for this Beluga course. Today, we're generally going to be covering inequality path constraints. So this is going to be our last lecture in the kind of like by hand classical optimal control theory stuff. On Friday, we're going to cover kind of newer methods that Beluga utilizes to more or less get what we're going to cover today. But it's a good background to have, just so you know what you're fortunately missing. So before we start, I could have covered this. Well, actually, this is usually more advanced than this, but it's good to cover now. And this is Pontryagin's minimum principle, or as he actually like posed it, is the maximum principle. He was a Russian guy, and in Russia, during, I assume still now, but during the Soviet era, they maximized things, while here in the West we minimize things. So we changed his maximum principle to a minimum principle. But really succinctly said is that so that the optimal Hamiltonian must be minimized over the set of all admissible controls U. So admissible means that, well, I guess it's the same as it always means, but it's the controls. Let me make this a vector to be clear. The controls that don't violate some inequality constraints. So the way that looks mathematically is you have H, which is dependent on T. The optimal, so every star, I think I covered this prior, but when I say star, that's the optimal. So the Hamiltonian with the optimal states and controls is less than or equal to any other Hamiltonian of the optimal states too, and then but of any other control for U within set of a big. So this is not super clear with my handwriting, but this is a small U, and then that's a big U, and these are this is the set of, this is one of those in the set of notation, and then big U is a set of admissible control. Okay, and then as I kind of already said, no, this does not imply that like that the Hamiltonian is minimized for any state. So see here, the x's don't have stars. So there might be somewhere that the Hamiltonian is smaller that isn't on the optimal path. But what this minimum principle only applies to is the optimal path. So I won't prove the minimum principle because I haven't actually ever read in full the proof of the minimum principle, because it's like a full book length proof. So even something that's so simple to state and simple to use is very difficult to prove. So I'm not going to do that here. Okay, so now we're getting to actual inequality constraints. And kind of the same as we did with equality constraints on the past. I'm going to start with inequality constraints on the controls. So we have some C of t and u, which is instead of equal to 0, this is less than or equal to 0. It's theoretically, if you wanted to make sure some value was greater than or equal to 0, you just switch the signs on C. So this is, you don't lose any generality with having the constraint this way. And like always, or like before, I guess, and I misspelled augment, but we're going to augment the objective function. So we have some Hamiltonian. So because it goes on the path, we join the constraint to the Hamiltonian, and then we have mu, which is Lagrange multiplier in C. And then if on constraint, so if the trajectory is on the boundary, then mu is greater than or equal to 0. Else, so this corresponds to C is equal to 0. Else, and then this corresponds to C is less than or equal to 0. Then mu is equal to 0. Okay, and then we can see that actually, the way we know that mu isn't less than or equal to 0, you can go back to that kind of significance of the different Lagrange multipliers that it's measuring its sensitivity. So basically, if you're on the constraint and mu was less than 0, then in that instance you should not be on the constraint then, because there's some area within the constraint boundary that you can satisfy to make the Hamiltonian smaller. So that's where this that condition comes from. And then the second condition comes from deriving like the necessary conditions that. So we have a normal one, and the only one that changes in this case. So we have the partial of the Hamiltonian, and that's expanded out. Okay, so that's our new necessary condition. And like all these I'm showing today, the problem is solved by piecing together constrained and unconstrained ox. So if you go back up here, right, so if this C is less than 0, that means that the constraint isn't active. And if mu is equal to 0, Hamiltonian is the same, means the problem is acting like it's unconstrained. And only when mu is some positive number, then we're going to actually be on the constraint boundary. So this turns two-point boundary value problems into a multi-point boundary value problem. hopefully if I get there in time, that will show up in the example we do at the end of this lesson. So, or maybe before we get there, this is a kind of oh, no, I'll get to it at the end. So we're going to cover bang-bang control, and that is the technical name we find in all the books. So for certain problems, this is especially with linear control variables. The optimal control will reside on constraints boundary, and this makes sense. So like if you insofar as if you have a linear control, then you're always going to want to, not always, that's wrong to say, but it's likely that you're going to want to maximize it or minimize it, and because you don't have some other, because it corresponds to the states in a linear way, that chance is much higher than if you have some control that doesn't interact with the states in a linear way. And then what makes it bang-bang is that at certain points, the control may switch from one boundary to another. And then this is bang-bang control. So what that may look like is, say you have some U here and some T, and it's constrained. So you have like an upper limit and a lower limit. Your control might go like this, and then instantaneously. So I probably even shouldn't connect it. You might switch down, and then up, and then down, right? So see how these jumps, you can imagine if you implemented this in a machine, that it would basically hit the limits back and forth really quickly and make a lot of noise, and that's where the bang-bang comes from. So I'll show kind of why that happens. So we consider, so this is kind of an example problem, but it's generic. So we have some x dot, and this is a linear system completely. So we have some A matrix and some B. So this is a normal linear system. And then we have some bounds for U between -1 and 1. So we want to minimize time from some initial conditions to origin, and that's where x is equal to 0. Maybe I should say x of df is equal to 0. So we get a path cost of 1, because if you integrate 1 across the entire time domain and you want to minimize that, excuse me, that's how we do it, right? Well, yeah, I've shown this kind of minimum time path cost thing before. And then now we're going to, just for simplicity's sake, consider A and B constant. So Hamiltonian then is 1 plus lambda times internal dynamics. But if we take like the fourth, so normally what we'll do, right, is take the partial with respect to u. But what does that equal? That's equal to 1 plus lambda times a, no, yeah, one, not 1. It is, sorry, it's just lambda t b, but this doesn't have u in it. So we can't solve this for u and get our control law. So we can't use dh partial of h with respect to u equal to 0, because u disappears. So then that means we must use the minimum principle. So if we just look up to the Hamiltonian again, for a given x, if lambda transpose b is less than 0, then to minimize h, so if lambda transpose b is less than 0, we want u to be as great as possible, thus to subtract the most from the Hamiltonian. So therefore, u would be on the positive boundary, which is 1, and then vice versa. If lambda transpose b is positive, we want u to be as negative as possible, which is -1. So writing that out mathematically, so it's 1. If this is negative, it's -1. Oh, this is a b here. Positive. And notice that we don't have a condition. It's undefined if lambda transpose b is 0. And then we'll get to that condition later, but yeah, so I could just put undefined here. It's probably more complete than what I have. But for this problem, as posed, you should only be there on it, that undefined behavior should only occur on an instantaneous time, so it doesn't really affect the solution. But there are problems where such a thing does affect the solution. So this lambda transpose b is referred to as a switching function. Because as it changes sign, the control goes from one boundary to the other. And then we also have conditions as usual. So we have our co-state dynamics, and this, to determine our terminal time, we have this condition as well. Okay, so that's that. So now we're going to, like we did with the equality path constraints, we're going to add in states to the constraint. Okay, so it should look nearly identical. One said we have the state vector in there too. And that's less than or equal to 0. So we handle in the same way as previous problem, and then that's to adjoin this to the Hamiltonian. So we have our Hamiltonian with the addition of Lagrange multipliers times this constraint, and then like before, mu is greater than or equal to 0 if c is equal to 0. Mu is equal to 0 if c is less than 0. So yeah, like before, we get our DHDEU equal to 0, necessary condition. But then we also get an additional addition to the co-state dynamics, which is the negative partial of the Hamiltonian with respect to the states. But then we get the the additional constraint term. But if we apply this kind of rule for mu, we only need to consider the problem changed if c is equal to 0, and in ox where it isn't 1 is less than 0, we get our normal dynamics. In like the previous problem, constrained, unconstrained, ox must be pieced together. And then that's, I think as I said before, that's a multi-point boundary value problem. Okay, is there any questions so far? Okay. So proceeding forward, there's a kind of a side. So remember that undetermined behavior if the switching function was 0. Well, that's a specific case of a kind of more general case of what 342 is a singular arc. And what these singular arcs are is areas where, where the partial derivative of the Hamiltonian with respect to u is 0, and where it's the second derivative of that is singular. So if you don't remember your linear algebra, singular means one of the eigenvalues is 0, so the matrix kind of acts like 0. So you can invert it. So where these both occur at the same time, I guess I should get rid of this where I'll refer to as singular arcs. And then this is actually, if you remember, we had singular problems in the parameter optimization way back 5 weeks ago. So this is like kind of the same thing happening. So given our normal necessary conditions, we don't have enough information to solve the problem. So in other words, neither the normal necessary conditions, so that the HDU is equal to 0, nor the minimum principal are adequate to determine the optimal control. So I'm not going to go into too much detail of this, but traditionally when you have these problems, what we need is higher derivative information. So for that, we can use the generalized Legendre Clebsch condition. What that looks like. So it's actually so basically, and then, yeah, let me finish it, and then I'll talk about it a little bit more, but yeah, so we have this condition here, which basically, similar to the way we handled state-only constraints, here we take even time derivatives of the first partial of the Hamiltonian with respect to u until the control appears explicitly, and that the partial with respect to u of that switching even and odd is greater than or equal to 0. So basically, yeah, you take this expression and you keep on increasing q until you get the control to pop up, and then we can use this to solve for the control law. And what this is providing us is higher order derivative information. And that, yeah, so there's a lot more that can be said in, like, you know. Okay. Yeah, and Shitich said that it's also called Kelly's condition. It shows up in a paper by Kelly in the 60s. Yeah, so it's yeah, all this stuff is kind of explained more in Bryson and Hull's book, and then also Langutski's book. But it's kind of out there, and you don't need to know it super well now with our new techniques, which I'll teach on Friday. But it's good to know of its existence. So then, if there's not any questions, I will move on to inequality constraints on state variables. So we have some S of Tx is less than or equal to 0. So note that the control does not appear explicitly. But as we did last week, we convert to an inequality constraint of control and state variables by taking derivatives of S until U appears explicitly.
I am curious, why did you switch notation from C to S?
Because in the kind of lecture notes that I'm basing these lecture notes off of, and going back to my notes, that was the notation used. So C broadly means I think is for control, and S is for state.
Oh, okay, makes sense.
That's correct.
So, yeah, as before, we have a new constraint that's S, the qth derivative of S. This is based on T, X, and U, and that's less than or equal to 0. And then that acts as C of T, X, and U did. So we have, as a result, we have our joined augmented Hamiltonian. But then we have something else, like the inequality constraints, to ensure that the system is on the constraint boundary. We must also enforce the interior point constraint. So I've been using 5 for these. Actually, to a notation note, the notation in the notes that when I wrote this stuff was N, but I to be consistent, I think it's more consistent just to use different psi's. So some psi I. So we have psi of T of X, and then we, like the interior point constraints before, we apply that in the middle of the trajectory. Well, actually, I'll get to that where we apply it. But yeah, we have all the prior derivatives equal to 0.
And these are derivatives with respect to time?
Yes.
Okay, just checking. Thank you.
It matches what we did with the equality constraint. Because, as we'll see, you apply, so when you have your unconstrained arc, the system acts like the constraint doesn't exist, and then you have your constrained arc, and then it acts like an equality constraint, and then you have your unconstrained arc, in which it, well, you can have a switch between constrained and unconstrained arcs. Yeah, like kind of, it depends on the numbers actually in the problem, but you don't necessarily know a priori what the ordering of those arcs are. But yeah, so we apply this interior point constraint at either the beginning or end of constrained arc. And then just for simplicity, you could do either one, because if on that constrained arc, the constraint's the highest derivative of the constraint's going to be 0. So that means all these other derivatives will be 0, regardless of where you put this interior point constraint. I think technically you could even put it in the middle, but that's not what you, I mean, that would just make your life more difficult. But for simplicity, we're just going to choose the beginning. And then wherever you apply this constraint, a co-states in a Hamiltonian may be discontinuous. But it could be continuous at, well, it should be continuous at the other end. So in this case, yeah, so these two might be discontinuous at the application of so if you, so I'm just writing out what I said prior, but if you remember from when I taught interior point constraints, what is discontinuous tends to be what is constrained. So, well, that doesn't tend, it is what's constrained. So you have, if your constraint contains like some, so you have, your problem has some x value, and if x is constrained in some way or shows up in the constraint, you could expect at that, when you enter the constraint, that the co-state of x is going to jump. Likewise, if time is constrained in some way at that interior point, then you could expect your Hamiltonian to jump. Okay, so now I'm going to do an example of the state constraint. This is a relatively simple problem, but you can see it kind of how tedious it becomes. So we have we minimize j is equal to 1/2 the integral of from the integral from 0 to 1 of u squared dt. And then we have the derivative of x1 is equal to x2, and the derivative of x2 is equal to our control u at x is 0. We have our control is our state's equal to x1 at 0 is equal to 0, and x2 at 0 is equal to 1. And then we have at time 1, we have our first state is equal to 0, and our second state is equal to 1. And then we also are introducing the state constraint, that is x1 minus L is less than or equal to 0. Before we solve the constraint version, we're just going to assume that L is big enough that the solution doesn't violate the constraint. So first, assume solution does not violate constraint. Oops. So we have a Hamiltonian. Okay, from the Hamiltonian. And this is just like a normal unconstrained problem. Oops, that's not you, that's x1. So the first costate is its derivative is equal to 0, so that means the costate is constant. Excuse me. And then we have a second costate rate, and then that is equal to that. So then we have 2 is equal to negative ct plus d. And then we have our optimal control law. dHd, partial of h with respect to u is equal to 0. So therefore, u plus lambda 2 is equal to 0. So from that, we have u is linear ct minus d. If we integrate some things together, or substitute and integrate, we get x2 is equal to 1/2 c t squared minus dt plus e, and then we get x1 is equal to 1/6 c t squared minus 1/2 d t squared plus e t plus f. So to find our constants, we get at time is equal to 0, x1 is 0, that means that f is equal to 0. x1 at time 1 is equal to 0, so therefore 1/6 c minus 1/2 d plus e is equal to 0. We also get a constraints on x2, so x2 at 0, that is equal to 1, so then we know that e is equal to 1, and likewise we get x2 at 1 is equal to, well, I guess this is a negative 1 up here. I mislabeled this. Apologize about that. So this is equal to negative 1. So then, therefore, we get 1/2 c minus d plus e is equal to negative 1. We substitute things in to each other, and then we get d is equal to 0, d is equal to 2. So finally, we get optimal state of x1 of t is equal to negative t squared plus t, and then we get x2 is t is negative 2t, so that's linear, and then u of t is equal to negative 2. And then we could find the max value of x1. So this is, we get a sense of what else would violate our constraints and which ones won't. Not even a sense, like we could tell which else violate our constraints and which ones wouldn't. So we take the derivative of x1 with respect to time, and then we get negative t plus 1 is equal to 0. Therefore, this t is equal to 1/2. Which you expect, this is a symmetric, very symmetric kind of problem. So x1 max occurs in the middle, and then that's equal to 1/4. And just so we see, let me pop that out. So we have x and t, well, this is x1. We have a parabola does that. This is 1 and this is 0. And then up here, so this is at 1/2. And then this is 1/4. So what we want to do, what we're going to do next is we're going to make L equal to 1/8. So in that case, we know that the problem is then going to be constrained. So from that, so let me go here, set L is equal to 1/8. So constraint is active. And we can kind of guess at what that will look like. It will go up like before, not exactly like before, but it'll go up. Maybe actually it's a different color. It's not the best different color. Let's use this one. So it'll go up like before, then rise its constraint boundary, and then go down. So here it's fairly intuitive that we have some unconstrained arc, a constrained arc, and an unconstrained arc. So let's label this T1, and then this is T2. Let me say unconstrained, constrained, and then this is unconstrained. Okay, so let's start the problem. And this is going to have like nastier numbers, so just bear with me. And if the number is wrong here or there, it doesn't actually matter because you should get the point. So for between 0, time between 0 and T1, we have, by doing the same math as before, you have x1 is equal to this constants. And I noted the constants with a 1 because this only applies on this arc. And E plus F1, and likewise x2 is equal to like we had before. Since this is an unconstrained arc, it's like the problem has the same form, it just has different constants. So applying the initial boundary conditions for x1, we get f1 is equal to 0. Applying them for x2, we get e1 is equal to 1. So that simplifies things a little bit, but not entirely. So 1 there. Okay, and then we need the interior point constraint, which we're applying at T1. So at T equal to T1, we have our original state constraint, which is x1 T1 minus 1/8 is equal to 0. Then we have the derivative of that, time derivative, and then that's x1 dot, which then that is equal to x2. Therefore, x2 at T1 is equal to 0. And then the second derivative in which the control appears, we get x2 dot, which then is equal to u, which then is equal to 0. Therefore, the control at T1 is equal to 0. So we still have 3 unknowns in our equations here, but then we have 3 equations. For 3 unknowns, C1, D1, and T1. And if I'm wrong with these numbers, I'm sorry. This is what I had in the original notes. But we have C1 is equal to 128/9. D1 is equal to 16 thirds. And T1, and this is actually the one that kind of matters. It doesn't, I mean, these are just numbers, they're bound to change. But then we have T1 is equal to 3/8. And as a side note, here we were able to solve independently of the costates. Otherwise, adjoin, so yeah, if join interior point constraint. So this is a fairly simple problem, so we didn't actually need to deal with costates at this point to see how much they changed at that point, like at T1. But if you're doing a more complex problem, you actually have to go through the interior point constraint kind of things and use those necessary conditions to determine how much the costates jump and whatnot. So, excuse me, to figure out which costates jump and which ones don't. Okay, so yeah, so as a result, just plug in those numbers from above. I think these 50. And I know these can be simplified. And then this is for 0, T to T1. Okay, so actually now what we're going to move is to the last arc. So trajectory leaves, constraint, boundary at T2. So for T2 less than T less than or equal to 1, we do basically the same thing as before. So yeah. So here our constants are different than before. But the equations are otherwise the same. And then we have conditions at the end of the trajectory, which is x1 at 1 is 0, next 2 at 1 is equal to -1. For kind of symmetry reasons, we can, and just because it's easier, we can actually rewrite all this stuff on the back. So from TF is equal to 1. So what we do here is we have x1. Yeah, we just kind of shift everything. We have C2 prime, and then we could do T minus 1. So actually this isn't described in the notes so much, well, actually, then you have additional 3 conditions. So at t is equal to t2, and this is how you would solve for all those constants. We have t1, t2 is equal to 1/8, because it's on the constraint. And then from the other, we have the other constraint conditions that hold throughout. We have these. So x2 is equal to 0 and u is equal to 0. So we have 3 equations for 3 unknowns. C2 prime, D2 prime, and T2. And yeah, the notes I had from which I got this problem didn't have C2 prime, D2 prime, and T2 written out explicitly, but you could actually use symmetry. And I think that either the same as the previous one, so C1 and D1, or they might be negative. I don't know. It's not, yeah. At least all I've shown is that you can solve it for them. And then we have the one constraining arc, but that's the easy one. So we have between T1 and T2. The trajectory lies on constraint boundary, on the constraint boundary. So that's simple. That's actually these 3 conditions here. So we know x1 of t is equal to 1/8, x2 of t is equal to 0, and u is equal to 0. And then just to plot it up, to finish up, like to finish here. So let me add in our constraint first. This is at 1/8, and then I actually know the t's as well. So this would be 3/8, and then 5/8, and actually counting these out, I don't know why, but so that's 1 and this is 0. So what happens is that this goes up as expected in that cubic shape, right? And then it stays on this constraint boundary, and then symmetrically goes down. And then, yeah, you could cut this in the middle, right? 3/8 and 5/8, and there's no reason why this shouldn't be symmetric. Yeah, so that's the solution to this problem. But notice how instead of being able to solve it on one arc with the 2-point boundary value problem, we needed a 4-point boundary value problem. And then that's all I have for today. And that concludes kind of handwritten optimal control lessons. Any questions?
Will the Beluga problems for lectures 6 and 8 be up on the GitHub soon?
So the actual code and stuff, I'll try to update that after this meeting. I'm just behind, kind of super busy time, and I apologize for that. I'll try to get things up to date as soon as possible. The notes and the practice problems are going to probably come up in the weeks, like later weeks, and hopefully in the future, if I give this course or someone else gives a course, they'll have it for each particular time. But it's kind of just difficult for me to keep up. But yeah, I'll try to update things. Definitely the things I have. So these notes and then the lectures should be up by the end of the day.
All right, thank you.
Sean?
Yes? Yes, Vincent?
No, I was just saying thanks.
Oh, thanks. I thought you said I only heard Sean, so I thought you were about to ask your question.
Well, thank you for doing the lecture today.
Oh, you're welcome. Okay, well, it looks like you guys get 20 extra minutes of your day. Have a good Wednesday.
Thank you, Sean.
See you
Good
tonight.
Friday.
Thank you.